Hello, YouTube! Today we're going to do the beginning of our forces unit. Pretty much, we're going to talk a little bit about what a force is, and then we're going to talk about what forces do via Newton's first law. Next few videos are going to be covering the three basic Newton's laws on what forces are and how they work, and then we'll go into actually using them. So, end of the day, hopefully you should be able to use Newton's first law to predict roughly what something's going to do. There's not really going to be any math. It's just going to be like, well, there's not going to be a lot of math, but it's mostly just going to be about how do things actually function around forces. So the first big one is being able to break down and explain each part of Newton's law. The second big part is being able to identify if an object is accelerating based on like having the situation described. And then the third one is being able to put those two things together and then see what that acceleration does or does not tell us about the forces on the object. Let me just get my computer a little bit better set up. Great. So, as a few reminders from last unit, in particular, if you say that something is moving, what you're talking about is the velocity. So if you say something's moving to the right, that just means the velocity is pointed to the right. If you say something that's moving to the left, it means its velocity is pointed to the left. Additionally, if you're talking about something changing speed or you're talking about something turning, then you're talking about acceleration, not velocity. So anytime you say that something's accelerating, what that means is it's either turning or changing speed. It actually doesn't necessarily mean that it's moving, and it definitely doesn't mean that it's moving in the direction that you say it's accelerating. So if something's accelerating to the right, that means that if it's also moving to the right, it'll speed up. If it's moving to the left, it'll be slowing down, and if it's moving in any other direction, it'll be turning. So the really only situation that has something not accelerating is if it's moving at a constant velocity. Or I should say, more specifically, if it has this constant velocity. One very special case of that is if it's staying at rest, which means it's not moving at all, and it's staying that way. That last bit's important. Then that means that its velocity is constantly zero. But being at rest doesn't necessarily mean that it'll stay that way. So, for example, if I just take something and I throw it up into the air, if I throw it straight up, then when it gets to the very top, there'll be a moment where it goes from going up to stopped to going back down. If you think about the velocity graphs from last unit, it'll be the point when it starts crossing the line, even if it has a constant acceleration. That point where it crosses the line, it still has a slope on the line, it's still accelerating, but it's not moving. So just because something's not moving doesn't mean it's necessarily not accelerating. Now, if it is accelerating and it's not moving, it will not stay that way. It'll start moving, but for a brief instant, it'll be at rest while accelerating. So just something that's a little counterintuitive that winds up having some pretty big ramifications for how people approach the rest of the unit. So just starting out, what's a force, right? So we're going to spend the entire unit talking about forces. Probably should know what they are. Really basically, it's just a push or a pull. So if you're saying that there is a force on something, that's talking about how much the thing is being pushed. If you're saying that there is a force of something, you're saying that that is how much of a push the thing is making. If you are using force in such a way that you can't immediately just replace it by using the word push or by using the word pull, then you're probably not actually using the word force correctly. So I guess just be careful for that one. Uh, because of that, there's sort of some meanings that people use the word force all the time. Momentum is another one where they use it all the time to not quite mean what it actually means outside it. Like, sorry, when you use it outside of physics, normally you don't mean quite what it means inside of physics. So just be aware that it's way simpler than you think it is, but also that means way narrower and way more specific than you think it is. It is just something that is pulling or pushing, and it's the amount that it pulls or pushes. Um, Newtons are the measurement of force. So when I write 0 newtons, which when I write it should look something like this, that's not the word on. That's saying that the force is 0 newtons. Just as a getting ahead of that being a problem. Technically speaking, there are four fundamental forces. So there's gravity, electromagnetism, strong force, and weak force. Um, we don't really deal at all with strong force or weak force. We deal with gravity and we deal with electromagnetism, but not using the KQQ over R squared law. We actually just deal with electromagnetic force because, like, pretty much everything we talk about are the electrons from atoms pushing off each other, and that's electromagnetic force. So, not super important, honestly. We're not going to care which of these four it is. We're going to be talking about different subsections of these, but like, technically speaking, every force we talk about is broken up from one of these four types. Okay, so what does pushing something do, basically? And this is us sort of trying to figure out um, how does, like, what do forces do? So if you for some reason have like a little cart or something with wheels that you can push, I would recommend taking a minute to just sort of take it, push it, and see what happens. In particular, what I want you to focus on is, if you aren't pushing it, what does it do? And when you do start pushing it, what does that do? In particular, in order for you to be pushing something and actually putting a force on it, you're going to have to be feeling it. So is it possible, for example, to push the cart while you're feeling it and have it slow down? Is it possible to make it speed up? Is it possible to push it while you're feeling it and have it go at a constant speed? Is it possible to push it while you're feeling it and having it turn? And in particular, what you should find is that if you're pushing something that's moving and you push it from behind, it'll wind up starting to speed up. And if you push it from the front and you try pushing it against the way it's moving, you should find that it slows down. And if you push it on the side, you should find that it starts turning. And if we think about those three things, speeding up, slowing down, and turning, those are the three options for acceleration. And that's Newton's first law. An object at rest will remain at rest, and an object in motion will remain in motion at the same speed and in the same direction. So all of that is one thing. Unless, and then here's the second half, acted on by an external unbalanced force. Or it might actually be better to say external unbalanced forces. But one force could also do it. So, taking this and breaking it down, because there is a lot here. So, at rest will remain at rest. What this means is that things don't start moving. Starting to move is a change in how you're moving. So, in particular, what this is saying isn't that if nothing's moving, this isn't saying nothing will ever move. I really want to focus on it. This is saying nothing will start to move, and you should think of that as a special case of nothing will change its velocity from 0 to not 0. So we're really talking about that change from 0 to not 0, not talking about whatever happens afterwards. And an object in motion will remain in motion at the same speed and in the same direction. So what that is saying is that nothing ever changes its velocity. So we've got two big things here. Things will keep moving in the direction that they're moving forever. If that happens to be that they're not moving, they'll stay that way forever. That's the first half of this statement. Second half of this state, which is to say basically that nothing ever accelerates. So if we take all of that and we just simplify it down, nothing accelerates. What tends to be weird about this is that the thing that you see when you're watching an object is movement, is velocity. So if you're thinking about watching something and watching what happens to something, this is not going to track with how this law works and how what's happening behind the scenes actually works. The other big thing that's a little bit weird about this is going to come up when we get to the second part, but nothing will ever accelerate. So things will just keep going forever, and things will not start going unless we've got a push or a pull that's from something else, so it can't be pushing itself, and it has to be unbalanced. When I say unbalanced, what I mean is that there isn't something going the exact same amount in the exact opposite direction that's balancing it out. You could have multiple forces doing that. So in particular, if we look at this first one is balanced because we have 3 to the right, 3 to the left, and those two will cancel each other out. Our total will be 0 is another way to think of that. If there's no forces on it, then our total is also 0. If there's 3 to the right and 3 to the left, then those two things together mean that there's no force in effectively, because they cancel each other out. So we've got a total of 0. If we look at this one, there are two forces that are the same as each other, but one of them is going up and one of them is going to the right. Those two things don't balance each other out because they don't go in they're not in parallel directions. And so this thing would have an unbalanced force to the right and an unbalanced force going up. And those two things together would mean that the force would be unbalanced in multiple directions. One thing that I quickly want to highlight here as well, one force can never be balanced. If you're thinking about a scale, right, and you only have things on one side of the scale, no matter what happens with that thing on that one side of the scale can't be balanced. Same thing with these forces. This will literally never be a balanced force. And just hang on to that because it tends to throw people off. All right, the unless part is also pretty hard, and it shouldn't be, but it is. What unless means is that if the first half is true, the second half is never true. And if the second half is true, then the first part is never true. So taking that with a sentence that is probably a little silly, but personally I think highlights why this is so weird. I am not saying that this is a true statement. Newton's first law is a true statement and the unless actually works. This is not a true statement. However, it's a statement that a lot of people wouldn't necessarily have an issue with unless they really start thinking about it. So let's really start thinking about it. The cookies will be delicious unless they're full of soap. So based on this statement, if we have cookies with a lot of soap, will they be delicious? Well, our statement tells us that the second half of the statement, full of soap, is true. So, because we've got the second half of the statement full of soap being true, the first half cannot be true. They cannot be they cannot be delicious. If the cookies are full of tar, then we actually don't know whether or not they're full of soap. Assuming they're full of tar but not full of soap, and I guess based on the word full, that means that you can't have other things instead. So if they are full of tar, they'll still be delicious because they're not full of soap. The second half of the statement is false, and therefore the first half of the statement must be true. If the cookies have just a little bit of soap, not a lot of soap, then they're also not full of soap. So even though there's soap in the cookies, they'll be delicious specifically because they're not completely full of that soap. Going the other way, where we're working based off the first half of the statement, if we have cookies that are just okay, then they're not delicious. And so because they're not delicious, they must be full of soap. Again, if that first half is false, that second half must be true. Additionally, if you have cookies that are amazing, then they cannot have soap in them based on this statement, which as we all know is untrue, and so our statement is false. Okay, so taking that and applying it here. What that means is our first half saying there's no acceleration, so acceleration is false unless there is an unbalanced force. So if acceleration is false, then force must also be false, because that first part of acceleration being false is true, which means that the second half of there are forces needs to be false. If we want to take that and make it a lot easier, if it's accelerating, there has to be force. Specifically, the force total can't be 0. But that also works the other way. If the force total isn't 0, it's got to be accelerating. So, personally, the way I phrase Newton's first law is literally just unbalanced forces cause accelerations, and unbalanced forces always cause acceleration, and or I guess only unbalanced forces cause acceleration. So if something is accelerating, that tells you that there is a net force on it. Always. And if something is not accelerating, that tells you that the net force on it, which we'll get to what net means in more detail later, but just so you have it here and you have it written down, the net force on it must be 0, or the total force on it needs to be 0. As a reminder, the way something is moving right now is velocity. That doesn't tell you anything about acceleration. So if I tell you that something is moving to the right, you don't know anything about the way that it's accelerating necessarily, which also means that you don't know anything about the forces. Now, if I tell you that something is accelerating to the right, then all of a sudden you know that the force has to be to the right because that acceleration needs to be caused by a force in the same direction. So going through, doing some examples, I would recommend taking a sec, trying these on your own, and then checking back in with the answers. Is the total force on the object 0? Yes, no, or we can't really tell. So starting out with our first statement, an object is at rest. If something is at rest, we don't actually know. Because if it's at rest now, that doesn't mean it'll keep being at rest. So this one's a maybe. Now, if it's the question had said an object is remaining at rest, yes, there would be no net force. But if it's at rest, maybe temporarily, this one's going to be a maybe. An object is moving at a constant 20 meters per second to the right. At this point, we have motion. It's moving. That means there's a velocity. A constant velocity. If the velocity is constant, that means that the acceleration is 0. If it's not accelerating and the acceleration is 0, then the net force has to be 0. So this one is yes, there is no force on it. An object is speeding up. In this case, speeding up is a type of acceleration. So because it must be accelerating, there must be a net force. So the net force is not 0. And the forces are unbalanced. Maybe there's only one of them. Maybe there's one of them that's bigger than the others. Maybe there are 2 against 1 and they're all the same size as each other. So one thing to be a little bit careful of, net force of 0 does not mean all the forces are the same as each other, but it does mean that they cancel out. An object is turning. This is another example of acceleration. So once again, for all the same reasons, the net force can't be 0. An object is moving to the left. We don't know. Its velocity goes to the left. If it's speeding up, that would be an example of acceleration. The net force wouldn't be 0. The net force would be pointed to the left. If the object is slowing down, that means that the net force would be pointed to the right. If the object is turning, that means the net force is pointed some direction that's in some way perpendicular to the left. But we don't know. So this one is actually also a maybe. All right. If you go to the description, there's a YouTube video that I think does a good job of showing you some examples of this, especially what this looks like in space. One of the things that's so counterintuitive and confusing about this law is that there's basically always some form of friction or air resistance when you have something moving on Earth. So normally if you push something on Earth, it won't just go forever if you push something that's not moving, it'll accelerate, so it'll start moving. But it won't just stay at that speed forever on Earth, normally because it's dragging against the ground or there's air pushing against it. And so most of the time, you have this intuition in your head that you need to keep pushing it to keep it moving, otherwise it'll stop. That's not true because things need to be pushed to keep moving. That's true because it's being pushed that's making it stop moving, and you need to push to balance out the force to make it so that it's not getting pushed to slow down. So again, a little bit counterintuitive for Newton's first law, specifically because of that friction. I'll post the link in the description of this video of that friction. I'll post the link in the description of this video so that you can see a video where people have some stuff moving in space and you can actually see that it doesn't slow down. And even with nothing pushing it, it'll just keep going forever. In fact, specifically because nothing's pushing it, it'll keep going at the same speed forever. If something was pushing it, it would be speeding up or slowing down or turning. All right, so that's it. Thanks and goodbye.